All right, so today we're going to talk about this worksheet that you were supposed to do for today, or no, for last time. I don't remember. I think it was due today, but we started going over it in the last class. I didn't in the last video because I wanted to give you a chance, those of you at home, to try this on your own, even though some of you aren't doing any of it while you're gone anyway. So uh, this right here, again, two cyclists, cyclist A and cyclist B, that have a graph that represents their motion looks like this. And we're supposed to interpret what this means. So, first question, do the cyclists start at the same point, meaning same position? And then how do you know, if not, which one's ahead? So I hope that going back to what we talked about with the tumble buggy and our equations for the tumble buggy, that you remember that the y-intercept, where the line crosses the y-axis, is the position when time is 0. And the position when time is 0 is called the starting position, typically we would say. So, do they have the same starting position? I would say no. How do you know? Because B is higher up on the position axis, which means it has a y-intercept that's not 0. So it is further ahead of A. Now, here's the thing. B is above A on the graph, but don't say that B is above A, because to me that sounds like cyclist B is riding on top of cyclist A. That would be uncomfortable. So we don't use above or below when we're talking about motion. The graph, yes. So the graph shows that B is above A on the position axis, which means that B is ahead of A. I hope you're getting the graph language. The words that we use to describe what the graph looks like are not the same words that we use to describe what that means to the motion. So being higher on the position axis actually means further ahead. I hope you're catching that. So we got to be careful what words we use, because if you say that B is above A, or B is on top of A, or B is higher than A, I'm going to get confused because I don't know exactly what you mean by that, unless you give me some more detail, like B is higher on the position axis, which means it's further ahead. That fully explains what you're trying to say. If you just say that B is above A, I don't know. Like, to me, that sounds like cyclist B is literally on top of cyclist A, and that doesn't seem like that would work very well. So be careful how you word things. Question 2. At 7 seconds, which cyclist is ahead and how do you know? Well, we don't know where exactly 7 seconds is, but if this is 5, I would guess that 7 would be somewhere over here. And then I go up here to where the lines are, and I see that the A's line is above B's line over here in this area. And so if I, project that over to, I guess I could, oh, I can't even write on it because it's not that kind of graph. So if I could just, if I could do that and show that it's going over there and then this one's going over here, the A is going to hit the position axis above where the B hits the position axis, which means that A is at a greater position than B at time 7 seconds. So who's ahead? A, because A's position is higher up the axis than B's position, which means A is ahead. Notice I didn't say A is above B. I'm saying A is further up the position axis, which means it's ahead. A, that is. Get that? Hopefully you got that. And question C. Which cyclist is traveling faster at 3 seconds and how do you know? Now, this is where a lot of people mess this up because they look at where 3 seconds is. And again, it's not marked, but if that's 5 and that's 0, then you can assume 3 would be around here, closer to 5 than 0. And if you go up like this and you see that B line is above the A line, at 3 seconds. And so a lot of people said, well, B is faster because B is higher up than A is, and so that means it's faster. Well, does that really mean it's faster? What did we say tells us how fast something is? What did we say tells us how fast something is? The how fast part is steepness. The steepness is the how fast. So if we look back at this, which line is steeper? A's line is steeper. The whole time, A's line is steeper. So who's faster at 3 seconds? Does it matter who's ahead of whom? And again, they kind of trick you because the first question was about who was ahead. The second question was about who was ahead of whom. And now they're asking about who's faster. Completely different question, which means you have to look at something completely different on the graph. So it's not who's above who on the position axis. It's about who's steeper than who. And A is steeper than B. Therefore, A is faster than B the whole time. Does that make sense? I hope, maybe. I hope so. Next, are their velocities equal at any time? And how do you know? Well, that's kind of what we were just saying. Is the A line ever the same steepness as the B line? So do A and B ever have the same steepness? If you say no to that, then your answer to D is no. They never have the same velocity because they never have the same steepness. If they had the same steepness, what would the lines be? If both line A and B were the same steepness, how would they be? They would be parallel. They would never do what? They would never intersect if they were the same steepness. Okay? If they were the same steepness, they would never cross. So they aren't. A is steeper than B everywhere. So A and B never have the same velocity because they never have the same steepness. And lastly, what is happening at the intersection of lines A and B? Okay, at the intersection at 5 seconds, what is happening then? Because a lot of people, I'm sure, answered D, that they had the same velocity at that point, at 5 seconds. But do they have the same velocity at that point? No. What is the same, though? If you put a dashed line over here to the position axis, if you follow that over to the position axis, how many positions do they have at that one point in time? They have one value for position, which means they're both at the same position, the same place. They're at the same place. That doesn't mean they're going the same speed. It means they're at the same place. They don't have the same velocity. I mean, look at what happened here. I wish I could make a mark on this graph that you could actually see, but I can't. Oh, maybe I can. Will this let me write on this? Oh gosh, horizontal, right there. Okay. A did this. Boom. A had that much position change. So A's delta X, if I can write that here, A's delta X is big. Okay. Now B, hold on, let me change the color here. B started here and went up to here. They're both at the same place, but B started way further up on the axis. Oops. Oh gosh, what am I doing? What am I doing? Erase that. Back to the pen. B's delta X is short. So B only changed positions by this much. A changed positions by that much. That's way different. Do you see? A had much more change in position in the same 5 seconds than B did. So A is faster. It's just plain faster. Even though they're at the same place, A went further to get there in the same length of time than B did. I hope that makes sense. So they're at the same place. Now, that still doesn't answer the question. The question is, can I scroll? I can't even scroll anymore? Oh, no. I can't even scroll. Why can't I scroll? Because I wrote on it. Oh, gosh. Can I erase it now? If I erase it, can I scroll? I don't even know. Oh, gosh, the video's just getting longer now that I'm doing this. Can I scroll? I could have just done that. I still can't scroll. Do I have to close the tools? I still can't scroll. Why can't I scroll anymore? Can I get out of that? Okay. Can I go back? Can I scroll? I still can't scroll. Okay. I don't know what's going on. I stopped being able to scroll because I wrote on the board. Oh boy. That's not good. Okay. So anyway, the question was, oh, this is not going to be good. Can I scroll down this way? I can't even do that. Oh no. Can I get out of here? Nope. Oh no. I don't know what I did. All I did was write on it, and then I stopped writing on it, and now I can't move the screen. That's no good. So anyway, hey, sorry about that. What's happening at the intersection point? I would say that, well, hold on. Who's faster than who? A's faster than B, right? Who is ahead before 5 seconds? B. Who is ahead after 5 seconds? A. What happened at 5 seconds? I would say that A did what? A passed B. Do you see that's what's happening here? Before 5 seconds, B was still ahead. After 5 seconds, A is ahead. So at 5 seconds, when they were at the same place, that's when A passed B. That's how I would word it. And now, of course, I can't even get out of this. I can't get out of this. I need to scroll. I need to scroll to the next page, but it won't let me. Oh no. Can I scroll on this? Okay, I can scroll on this one. Oh gosh, guys. I don't know what's going on. What if I do this? Can I go back to this? And will let me scroll? Now I can scroll. Whew, that locked me in there. Okay, so now the second graph. Now they say, okay, how does the motion of A in this graph compare to the other one? Well, I know they're not side by side, but A in the first graph, A in the second graph. How do they look to you? They look the same to me. Same steepness. A is still tipped up the same way. So I would say they're the same to me. Yeah, I hope. Same. Now, how does the motion of cyclist B in this graph compare to B in the previous graph? Okay, so now how does B compare to this one, to this one? This one to this one. Well, what kind of slope is this? That's a negative slope. Negative slope means what? Negative slope means what? Negative velocity. So it's going the other way. If you look at the y-intercept, B started about right here last time. Now it's even further up. So it started further ahead than it even was last time, but it's going in the other way. It's going the other way. Yeah? Hope that's what you said. And C, which cyclist has a greater velocity and how do you know? Well, again, velocity, how can you tell which one has a greater velocity? Remember, velocity is the slope. The slope of a position time graph is velocity. How steep are these? Is one of them steeper than the other? Sure is. A is way steeper than B. So who's faster? A is still faster. It doesn't matter that B's slope is negative. We're just looking at how steep they are. Okay, regardless of how B is tipped, positive or negative, that doesn't matter. It's just how much they're tipped. And B's is not tipped very far. A's is way steeper, and so that's way faster. D. Describe what is happening at the intersection of lines A and B. Now, in the last one, since they were both going in the same direction, we said that A was passing B. Now they're doing this, opposite directions, which means I would probably not say that A is passing B. I'd probably say that they are what? They're passing each other, is how I would say it. A and B, they're passing each other. That's usually how we say it when two objects are going in opposite directions and they go past each other. That's what we say. They go past each other. It's not one passing the other. It's they go past each other. Does that make sense? Hopefully. And which cyclist has traveled further during the 5 seconds, and how do you know? Which one travels further in the first 5 seconds? Now I'm going to use the pen again, which is probably going to lock me in again. And so if this is where they are, and I draw a little dotted line over here to the, oh gosh, I went up the hill a little bit there. Oh geez. Right there, ish, something like that. This is B. B went from here to, drawing a bracket. Oh no, on the trackpad, that's tough. Boom. Okay. Hold on, I can erase that. Okay, good enough. And so that is B. A goes from here all the way up to here. So that's A. That's how much position change A has. This is how much position change B has. Pretend that's a B. Obviously, A went way further, way further. B just did this, tiny little bit, probably even less than it did in the first one. So B may even be slower in the second graph than the first one. It's hard to tell because, we're not looking at graphs that are side by side. And we don't have any numbers to find the steepness, but that's not very much position change. A went way further in the first 5 seconds. Again, further reinforcing that A is faster than B. I hope that makes sense. Now, where was I? I got to go to, so that was this assignment. We talked about this assignment. Then we started talking about motion maps. All right, so we started talking about motion maps. And we were looking at this. Okay, so here's what I did. I had to tell people about motion maps. Motion maps are these things that we will use that give us kind of a picture of what's happening in a graph. So if this is the graph, I tried to recreate the graph, as it was on the worksheet. And I said, okay, we need to come up with a way to diagram the motion. It's called a motion map, so that we can show what it actually looks like. And in fact, we did the tumble buggy thing in class. So I actually had the slow buggy, which was group 3's buggy was the slow one. And we had it set up as cyclist B. And then we set it up on a counter, and then on a lab counter, and then we showed one tumble buggy racing the other tumble buggy, kind of like this case here. So then we decided we needed to come up with a way to make a diagram of that motion. And so that's called a motion map. So I'm going to show you how it looks. First of all, you make oh gosh, I'm just going to have to show you the whole thing, I guess. First, you make a vertical line. The vertical line is like the 0 position. That's like the 0 position. That's like the start line. And you mark it with a 0, and then you show which direction is positive. We typically say to the right is positive, and so because the right is positive, we mark it positive with our little arrow here, okay? Now, A started at the 0 position. It shows it on the graph, right? A starts at the origin or the 0 position. So I put a dot that represents A. And then I make arrows for A. And arrows are nice for representing velocity because arrows have a length and they have a point. So how long they are tells us how fast, and which way it's pointed obviously tells us which direction. And because A has a positive slope, we make our arrows pointing positive. I guess positive. And because A has a constant slope, that means it has a constant velocity. That means all the arrows for A need to be the same what? Length. So that's A's motion described in a motion map. You can almost think of it as an aerial view. We're looking down on the motion here, okay? So we can see what these two things are doing, and they're going to be side by side. They're not going to collide like the lines do. That's telling us where the positions are. It's not the actual path they travel. That's what the motion map's kind of showing. So that's why A looks the way it does. And I made 5 dots because this is happening for more than just one moment in time. In fact, we have 5, not just 5 seconds, it's probably more like 10 seconds showing on the graph. And so if each dot represents like maybe 2 seconds in time, then that's 2 seconds, 4, 6, 8, maybe 10 seconds goes by, which is about right on the graph here. So 10 seconds goes by, and I have each arrow representing about 2 seconds. Then for cyclist B, that doesn't start at the origin, so I did not put my dot for B. Oops, oh boy. I did not put my dot for B on the 0 position. I put it out away from the 0 position on the positive side of 0 because the A line or the B line starts on the positive side of 0. Ahead of, now notice, it's not above, it's ahead of A. I did not put my dot for B up here. Oh gosh, why is it doing this? I did not put my dot for B above A. Okay, above on the motion map doesn't mean the same as above on the graph. Above on the graph means a positive position. Where's a positive position? Not up here. That's still 0. So we move the dot out away from the positive or away from the 0 position in the positive direction. That's where B first appears. And then B is traveling for the same length of time as A, but what is it doing? It's slower. So my arrows are shorter. Okay, shorter arrow means slower. And I have 5 of them still, but it's slower. Shorter arrows. Now notice, B starts ahead of A in the motion map. A goes past where B ends in the motion map. Just like the graph, A goes past where B is. A is further ahead at the end on the graph, and A is further ahead than B on the motion map. Okay, so these are some of the details. It's hard to explain what a motion map is without just showing you a motion map that coincides with a graph. Okay, so what I'd like you to do now is take a look at the second graph. So this is graph 2 from the worksheet. I want you to try to sketch a motion map for that. So pause the video, sketch your vertical line with your 0 and then your positive direction, sketch all that, and then try to draw what the motion map looks like for the graph 2 now. Pause the video, do that, and then come back and I'll show you what it looks like. So A looks exactly the same as it did before, right? Exact same thing. Because remember, A's line here is the same as A's line here. Same thing. B's is not the same. So if B started here last time, and we see that B is even further up on the position axis than it was before. It was down here, now it's way up here. What does that mean? That means it's starting even further ahead. But its arrows need to be in what direction? Negative direction, because it has a negative slope. Oh my goodness. So B is going to look like that here. Okay? B starts even further ahead, but then it's going in the other direction. So I hope this makes sense. I hope you're seeing that this makes sense. maybe. And notice B never gets back to the 0 position. Why? Because B never gets down to the t-axis. It never gets to the 0 position all the way. So it has to stop short of the 0 position on the motion map. So I hope the motion map thing makes a little bit of sense. Now what we did here is we had a red line here showing how one object might be moving, and then one where a blue line like this. So what do those mean? Well, the red line, it's kind of traveling like A was before, only it's even faster because it's steeper. Only it doesn't start at the 0 position. Now it starts with a negative position. So how do you show that in a motion map? I would do that. Negative position for the start, traveling in the positive direction because it's a positive slope, constant length arrows because the slope is constant, so the velocity is constant. So we have, I don't know which direction. Oh my gosh. This direction? Yeah, I'm trying to make sure that oh gosh, I'm the mirror image and oh sheesh. Anyway, that is like the red line, okay? It starts below the 0 on the graph, which means to the left of the 0, right? On the negative side of the 0 line. Now, how about the blue line? What is the object represented by the blue line? What is it doing? Is its position even changing? No. If the line doesn't go up or down, then the position is staying exactly the same. If the position stays the same, it's not moving. How do you show that on a motion map? Well, somebody in class mentioned we'll just put a dot, no arrow. That's kind of a weird shaped dot. Now, the next question I had was, well, but this is happening for more than just 1 second. Like this happens for longer. The blue thing is not moving for a longer period of time than what the red one is actually shown moving. So that's a long time. How do you show that this happened for a long time? So in class, I kept drawing dots over the top of the first dot, but you can't tell there's more than one dot there. So how do we show that on the motion map? Well, somebody said, well, then you start putting dots out here like this. I said, well, those are getting further from the 0 position. So if they're getting further from the 0 position, then how can I put multiple dots with no arrows, but it's getting further away from 0? Well, that doesn't make any sense. If it's not moving, the dots can't get further away from 0. So we decided that up and down would make most sense. Now, I put a lot of dots here. I mean, you probably don't need this many dots. I put a ton of dots. So the dots, if you measure them, or if you think about this, if you measure the dots from, oh, now this I can write on. If you measure the dots from here, oh, what the, no. I need a pen. Oh no! Now my screen is, or my face is in the way. I'm gonna do this. Oh, now I gotta. Oh gosh, this video is getting too long. So if I do this, are all those dots the same distance away from the 0? Are they all at the same position with respect to the 0 position? The answer is yes. They're all the same distance away from the 0. They're not going anywhere. So here's the thing, up and down on the motion map, it really doesn't have any meaning. It's like having a start line that goes right and left beside you, and you can have a bunch of different people all lined up at the same start line, and you're at the same place all along the line. So in this line here, again, that's like a start line all along the same line. So we can show that time is elapsing by putting dots on top, one on top of the other, that shows, hey, the person was not moving and this happened for more than just a second. I hope that makes sense. So next time we have class, there will be a quiz, okay? And here's what you need to be able to do for the quiz. You need to be able to find the slope of a position time graph and know that that's called velocity. You need to be able to know that the y-intercept tells us where the object was when the clock started. You need to be able to write the equation, the y equals mx plus b. You need to be able to write the equation of the line on a position time graph, which we did all of these things for the tumble buggy, right? We did these things on paper and pencil, and then we put the data into graphical analysis, and we did it there too. And then you need to be able to draw motion maps for the motion you see on a position time graph. So when we have class again, we'll do a little more practicing with that, but then we're going to have a quiz over those things by the end of the next block, whenever we have school again. Who knows? With weather coming, nobody knows. So anyway, that's what we did today. Hopefully that makes sense and makes maybe a little more sense than it did before. And I'm going to finally stop talking because this video got way too long. So have yourselves a great rest of your day and be safe out there.